Anin, Bojo, Sarah Hazel Dijnikas, Nabizing Donjaba. Thank you for joining me for recommended data collection procedures for locating unmarked graves using unmanned aerial vehicles or drones. Unmarked graves investigations can bring up distressing content, and it is important to take care of yourself mentally and emotionally while doing this work. Please make sure you have health supports in place, or you can call one of the numbers on the slide if you are feeling triggered, and you can speak to a health professional. And I'll just leave this up for a moment. Unmanned aerial vehicles, UAVs, and more commonly referred to as drones, and officially described as remotely piloted aerial systems, RPASs in Canada, are extremely useful for investigations at Indian residential schools. They serve two primary functions. One, primary investigation, where a variety of UAV-mounted sensors are used to try to identify buried features from the air, including unmarked graves and other buried archaeological features. And two, to generate maps to aid in the planning and execution of subsequent ground-based investigations, including GPR. There are many UAV options on the market that range in price from a few $100s for a simple quadcopter with camera, typically used for recreational purposes, to fully integrated multi-sensor systems costing over $20,000 that are used in the surveying industry. The level of accuracy and resolution will vary considerably between systems, so it is important to understand some of the basic differences. Choosing the right system will depend on your survey goals. Most consumer-grade UAVs are equipped with GNSS or GPS, capable of plus or minus 2 to 5 meters accuracy, and with a barometric altimeter that can be affected by varying atmospheric pressure and elevation, both of which introduce imprecision into the output from mapping flights. While this level of accuracy might be sufficient in some instances, such as generating maps for planning purposes, if the UAV mapping output is to be integrated with other georeferenced data as part of an investigation for unmarked graves, this level of imprecision might be problematic. It can be addressed in two ways. First, the use of professional-grade UAVs equipped with better quality GNSS receivers capable of differential correction, or two, establishment of ground control points, GCPs, prior to the UAV flight. GCPs are points on the ground that are identifiable in the images obtained in the drone survey and which have known geographic locations. The GCP coordinates are used to refine the positions of the photogrammetric output. In some circumstances, this will render results to accuracy within a few centimeters. This high level of precision and accuracy may be important when attempting to integrate diverse, spatially registered data within GIS software. UAVs come in fixed and rotary-winged configurations. Rotary wing UAVs offer the greatest utility because they are more maneuverable in flight. This includes smaller four-blade quadcopters designed for consumer use, as well as larger and more sophisticated 6- or 8-blade machines intended for professional applications. Fixed-wing systems are generally used for surveying very large areas. Lower-cost UAVs are usually equipped with built-in cameras, while professional-grade machines can interchangeably mount cameras or thermal, multispectral, and laser sensors, which is called light detection and ranging, or LiDAR. Drones find buried features with visible light, RGB or red, green, blue cameras, multispectral or hyperspectral cameras, thermal cameras, and digital elevation models or DEMs. Buried features are sometimes visible from the air through a phenomenon that archaeologists call crop or parch marks. These occur when grass or other vegetation directly above a buried feature grows or ripens at a different rate than the surrounding area due to the differences in the available moisture in the ground that are affected by the buried feature. This can result in positive and negative crop marks, where the vegetation is either taller and healthier, often darker, or shorter and unhealthy, often lighter. This difference in vegetation color and height is more obvious when viewed from above and can be recorded with standard RGB visible light cameras. Late summer, drought conditions, and evenings with low light and extended shadows are excellent times to identify features this way. While crop marks are often detectable to the naked eye, there are instances where we need additional help to identify them. Hyper or multispectral cameras, which record wavelengths beyond the visible spectrum, allow us to identify and enhance more subtle differences in the vegetation growing above buried features. Multispectral fluorescence and reflectance imagery is used to characterize plant health by identifying different levels of chlorophyll within plants. As noted above, plant health is influenced by the underlying soil and moisture conditions, which in turn can be influenced by the presence of buried features such as walls or grave shafts. Thus, plants growing directly above features sometimes have different levels of chlorophyll than surrounding areas. Multispectral survey is best performed later in the growing season after chlorophyll levels have had a chance to develop within plants. Thermal cameras and a technique known as thermographic imaging or thermography are another option for identifying buried features from the air. Buried features will absorb, reflect, and emit heat from the sun at different rates depending on their composition, density, and moisture content. For example, during a 24-hour period, the ground will heat up from the sun, which in turn can heat up features buried below the surface through a process known as thermal conductivity. At night, as the air cools, the ground surface and the features within it release heat. This will happen at different rates over different areas depending on thermal inertia, emissivity, and volumetric heat capacity of the soil and features. You may have noticed this phenomenon when walking from a grassed area to cross an asphalt road at the end of a hot day. You will still feel the heat coming off the road, even though the temperature has dropped. A thermal camera detects these differences. There are, however, some limitations. Firstly, buried features such as a wall or a pit are only potentially visible if there is sufficient contrast in the thermal properties between the feature and the surrounding soil. Secondly, this technique only works for features that are relatively close to the surface. It is important to understand, therefore, that we are not trying to identify the burials or coffins themselves, but rather the pits or grave shafts within which they are buried. Thirdly, while hypothetically possible, archaeological thermography has mostly been confined to the identification of relatively large, uniform features such as building foundations. Relatively little is known about its utility in the identification of unmarked graves. Thermal imaging is usually best done at night, as there is usually too much radiation from reflected sunlight during the day, which washes out any of the subtle thermal differences that different features might display. Unfortunately, it is impossible to predict how long after dusk the optimum time to survey is, as it will be different for each site. You might have to try at different times throughout the night to establish the best time. Buried features can also result in very small, imperceptible differences in the height of the overlying ground. While invisible on the ground, we can sometimes identify these small changes in elevation through the creation of very accurate digital elevation models, or DEMs. A DEM is an artificial rendering of the ground surface, which is viewed on computer software. DEMs can be manipulated in a variety of ways to accentuate minor elevation differences to facilitate their identification. There are two main ways of creating DEMs through UAV survey: photogrammetry and LiDAR. Photogrammetry is a process where computer software is used to identify thousands of common points in overlapping photographs to create a 3D model, through geometric intersection. The photographs are reoriented, warped, and mosaicked together into a single large image known as an orthomosaic. The second method for creating a DEM is LiDAR survey, which uses lasers to obtain very accurate distance movements. LiDAR systems send laser pulses downwards to measure distance to the ground. The sensor measures the time taken for millions of points of laser light to leave the UAV, strike the surface below, and then return. This three-dimensional information forms dense point clouds that precisely define the surface. LiDAR survey also has the advantage of being able to survey through wooded areas to obtain DEMs on the ground surface below the tree canopy. However, it is worth noting that contrary to popular belief, that LiDAR cannot see through trees. Rather, the laser light is able to penetrate through the spaces between the branches and leaves to survey the ground below if the tree canopy is not too dense. If light can get through, so can LiDAR. Because of this, it is always advantageous to survey when there is little or no tree canopy, as there are more spaces for the laser to penetrate. Early spring, before the tree canopy develops, is an ideal time to conduct a LiDAR survey. Flight planning is dependent on mapping objectives, site extent, vegetation cover, and airspace status. To collect imagery suitable for photogrammetrics processing, the UAV should be flown along transects at a standard height and speed as shown in this figure. Photographs are taken along these transects at intervals that allow standardized overlap between adjacent images. This is difficult to achieve using manual flight, but semi-autonomous flight planning software greatly improves efficiency and output quality. Most UAVs are equipped with sensors that enable safe and stable flight. They are controlled through two-way radio communication between the aircraft and the ground controller. The latter is usually paired with a tablet or cell phone to provide telemetry information and the UAV camera view. Many UAVs can also be programmed to fly in grid patterns while automatically collecting overlapping photographs like shown here. Using an internet connection, maps, often Google Earth, provide geographic context to identify the flight area. After assigning the flight elevation, degree of image overlap, and flight speed, the planning software automatically establishes flight transect lines. The completed plan is saved for upload to the UAV at flight initiation, whereupon it will automatically take off, complete the flight transects, and return to the landing zone. However, the pilot can regain manual air control at any time. The optimal flight elevation is dependent upon the preferred image resolution, the coverage area, and potential objects that might be hazardous to the UAV. Selecting flight elevation reflects a balance of considerations. Lower elevation flights generate high resolution images but require more photographs to achieve the required coverage. Higher elevation flights require fewer photographs, but at the expense of image resolution. Depending upon the camera used, a flight elevation of 40 meters will provide ground image resolution of about 1.5 centimeters per pixel, while offering a reasonable degree of flight efficiency and safety. Electrically powered UAVs usually offer between 20 and 30 minutes of flight time per battery, while newer, more expensive models can offer close to 1 hour of flight time. Since battery life varies with air temperature, wind velocity, and battery age, it is practical to limit flights to no more than 80% of estimated battery duration. The efficiency of semi-autonomous flight planning software can enable flights over smaller areas using only one battery. For example, an area of about 1.5 hectares flown at an elevation of 40 meters and at a speed of 2.4 meters per second will collect about 260 images within a 15-minute flight on one battery. The resolution of such imagery will vary depending on the camera used. The 260 images in this example would require about 2.1 gigabytes on the micro SD card installed on the UAV. When mapping larger areas, semi-autonomous flight planning software can accommodate multi-battery operations. UAV survey missions require a pilot and observers. In Canada, UAV flights are governed by regulations and licensing administered by Transport Canada. UAVs must be registered, and pilots must be licensed to a level appropriate for the airspace conditions over the survey area. The pilot controls the aircraft while the observers monitor the UAV and alert the pilot about approaching aircraft and other hazards. Most UAVs are equipped with sophisticated instruments to ease flying and to reduce crash risk. This includes a global navigation satellite system, barometric altimeter, compass, collision avoidance sensors, and a gimbal to reduce image motion distortion. Flight plans should be made in line with Transport Canada regulations prior to the survey to reduce hazards should something go wrong during flight. This might include the loss of sight or control of the aircraft and mechanical failure. Pre-flight planning also includes determination of airspace status over the survey area and gaining approval if the planned flight occurs in controlled airspace. Consideration of weather, wind and lighting conditions, and condition of the UAV hardware and firmware is also vital. Miigwech, thank you for joining me for this module on unmanned aerial vehicles. Please take care.